Hi class, in this session of Digital Principles and System Designs, we shall study about K-map or Karnaugh map, right? So it is another way of simplifying a Boolean expression. So far, we've seen how to simplify Boolean expression using Boolean algebra, and we have found out methods such as using the min terms and max terms to simplify an expression using with the help of the truth table. Let us see how we can use the min terms and max terms of sum of products and products of sum, map it around a K-map, and see how that works, right? So let us crack on with the lecture. So logic function simplification. Why do we do that? Like we've discussed earlier. So it's a simpler expression, so it uses less logic gate. Therefore, it's cheaper, it uses less power, and sometimes it's faster. Like I've already said, algebraic simplification can be used. It can be done using basic identities and theorems of Boolean algebra. It can be used by using the min terms and max terms. Also, Karnaugh map is a graphical representation or a graphical technique for simplifying an expression. The advantages of using a K-map or Karnaugh map is a more orderly process with well-defined steps compared with trial and error process, which sometimes is used in algebraic simplification. So this is like logically it reads better, and it's easier to understanding, and it's always able to produce a minimum expression. Disadvantage is maximum you can have 5 or 6 variables. More than that, it becomes really complicated, and using simple algebra, Boolean algebra, is much easier than using K-map. So, a K-map is described as a matrix consisting of rows and columns that represent the output values of a Boolean function. It can either be a sum of product form or a product of sum form. So, suppose I have a truth table here. Let us switch on the laser pointer. And it's just not working, so that's fine. So, if we have a truth table like this with just two variables, x and y, the possible inputs can either be 0 and 0, 0, 1, 1, 0, or 1, 1. So if we write it in terms of min terms, it's x dash y dash. The second one will be x dash y. The third one is xy dash. And the last one is xy. Now, I have a map here where my rows are signifying the x values, the column is signifying the y values, right? So both y and x can either have a 0 or a 1. So in the first block, which is the blue, when x is 0, y is 0, I get x dash y dash, which is my min term. When x is 0, y is 1, I get x dash y. Similarly, when x is 1 and y is 0, I get xy dash. And when x is 1 and y is 1, I get xy. Right? So we can easily see which min term contains common list rows. Right? So if you see the first row, it has got x dash that is common. If you see the first column, that has got y dash in common. So why is this important is that when you finally simplify this using De Morgan's law, you can, you get. So if it's a 3 variable, you've got x, y, and z. So like if it is 2, then one represents the row and the other one represents the column, right? So if it is 3 variables, one can represent the rows and the other two combined together can represent the columns. For example, I have my x as the rows, y, z as the column. So when x is 0, y is 0, and z is 0, I get x dash, y dash, and z dash as my min term. When x is 0, y is 0, and z is 1, I get x dash, y dash, and z as my min term, and so on. So I populate my K-map with all the minterms, or I can just write M0, M1, M3, and M2. Now, the thing that you need to really pay attention here is while we're writing a truth table, we write 0, 0, 0, 1, 1, 0, and 1, 1. However, in K-map, it's very important to make sure that between each box or between each row and each column, there's only one variable that's varying. For example, observe the YZ values the way it has been written. So 0, 0, 0, 1, 1, 1, and 1, 0. So, between 0, 0 and 0, 1, Z changes. Y is 0 on both occasions. Z changes from 0 to 1. Now, between 0, 1 and 1, 1, we can observe that Y is changing from 0 to 1. However, Z remains 1. Right? The last one, when it is 1, 1 and 1, 0, again we observe that Y remains constant and Z is changing from 1 to 0. So at any point, if we write our K-map in this fashion, if we populate our K-map in this fashion, at any point only one variable varies. Now that is an important property as long as applying De Morgan's law to simplify, right? So this is something that you should really keep in mind. So if I write in terms of minterms, I write M0, M1, M3, and M2 for the first row, M4, M5, M7, and M6 for the second row. So this is the arrangement that's usually used for a three-variable map. This K-map is written. So you have an option to write it this way. Just keep the A as a rows and B and C as a column. A as a column and B and C as a row. So this is very plausible way of writing. Or you can just take C as a row and BC as your columns. Anyway, however, ultimately the simplification should be plausible and it should obey all laws of how to simplify K-map. That's all matters. It doesn't matter how you write it. Okay? So if I write it this way, then my min terms and max terms are, for the first column, it's M0, M1, M3, and M2. For the second column, it's M4, M5, M7, and M6. So let us just have a look at an example where a three-variable truth table is given to you. You've been given A, B, and C, and you've been given the value of F. So I'm writing my K-map in such a way that AB represents the column and C represents the row. Just for the sake of, I just wanted to do something different, or to make you understand how versatile K-maps can be. In your own time, try using A as the rows and BC as a column and see whether you're getting the same answer, right? So here I have the min terms, which are that whenever F is 1, that is taken as a min term. So if I see when A, B, and C are 0, my F is 1. So in the very first block, the first row and first column, I put a 1 there. When A is 0, B is 1, 0, and C is 1, my function is 0. So that's the second block, or that's the first block of the second column. When A is 0, B is 1, and C is 0. So when A is 0, B is 1, and C is 0. That's the second block of my first row. So that is 1. So when A is 0, B is 1, and C is 1. So that would be my second block of my second column. Second block of the second row and second column. So that is also 1. So when A is 1, B is 1, and C is 0. When A is 1, B is 1, and C is 0. That is your sixth term. So my output is 0. And when A is 1, B is 1, and C is 1. That is my seventh row. Seventh input sequence. And that again the output is 0. So now I'm left with the fourth and the fifth input. Now both of them, they are 1, so I put 1s there. Now if you see, I can either group my 1s in horizontally or vertically. Diagonal grouping of 1 is not allowed here, because if you are grouping diagonally, then there are chances that more than one variable might vary. So either you can group them vertically or you can group them horizontally. So grouping all this, the first one is you have A dash C dash, because the first two blocks of the first row, you can see that B varies from 0 to 1. So B will not be considered. Remains constant, but it is 0. So I put an A dash. C remains constant. C doesn't change. So that becomes C dash because C is 0. Now if you take the second column, you can see that A and B remain the same. It's just the C that is changing. Again, A is 0. That's why you say A dash B. The last one, the fourth and the fifth min term, again you see that it is a vertical group. So A and B do not change. B is 0, so it becomes AB dash. C changes, so we do not consider C there. So ultimately, all you have to do is you have to add all these product terms. So F becomes A dash C dash plus A dash B plus AB dash. We know that A dash B plus AB dash is the exclusive OR function. So we can just replace that with an exclusive OR symbol of A and B. So in the next class, we shall discuss four variable K-map and discuss more rules and regulations to be followed to simplify K-map. I hope you had a fruitful session. Thank you.